Direct, analytical tone. True autonomous AI agents hit a hard architectural wall, the strict limit of the context window. Cram enough data tokens into this fixed space, and the system will violently crash. This graph plots the exact mathematical problem. Because transformers' self-attention requires every token to evaluate every other token, compute costs accelerate exponentially as context length increases. This is the O of n squared trap. Tech companies attempt to bypass this by paying for massive 1 million token context windows. But in practice, the models suffer from the lost-in-the-middle phenomenon, silently ignoring core instructions buried deep in the prompt. Treating the context window like a massive hard drive is a brute force tactic that ignores 50 years of computer science. To achieve infinite persistence, developers must stop treating the LLM context window as a hard drive and start treating it as highly constrained physical RAM. This is exactly what the MEM-GPT architecture and its open-source framework, LLM, are built to do. They port traditional operating system virtual memory management directly into the logic layer of a large language model. The architectural analogy is strict. The fixed context window acts as physical RAM, while external vector and relational databases act as unbounded disk storage. Standard retrieval augmented generation relies on a passive external wrapper to feed data to the model. Here, the retrieval mechanism is active, controlled entirely from within. The language model itself acts as the operating system kernel, making autonomous decisions about data orchestration. By controlling what stays in RAM and what gets written to disk, an agent with a small 4 kilobyte context window mimics infinite memory, bypassing the quadratic compute costs of massive forward passes. This block diagram maps the system's spatial layout. Tier 1 is the main context, the immediate working space, strictly capped by the token limit. We divide this RAM into 3 read-write zones: system instructions, a working context scratchpad, and a message queue. Across a strict logical boundary lies Tier 2, the external context, entirely invisible to the language model processor. It consists of recall storage, a vector database for message history, and archival storage, a relational SQL database holding static knowledge. Blind to Tier 2, the agent must selectively fetch and evict its own information. How exactly does data cross this barrier if a human developer isn't writing the code? It runs on an event-driven trigger. When the FIFO queue hits capacity, it fires a memory pressure interrupt into the main context. Recognizing this interrupt, the model autonomously outputs a JSON function call to swap data out of RAM. Specifically, it calls a summarize and evict function, precisely targeting the oldest messages. It recursively summarizes those old messages, distilling their semantic meaning into a tiny footprint pinned back into RAM. Simultaneously, the raw message data is vectorized and pushed to recall storage. The operation works in reverse. Detecting a gap in its working knowledge, the agent issues explicit semantic search function calls to the disk. That retrieved data hydrates the main context just in time to compute an accurate answer. This continuous cycle of dehydration and hydration, of strategic forgetting, prevents context pollution and allows the agent to maintain hyper-focused reasoning indefinitely. We can observe how this OS-style control flow handles complex queries by looking at the nested key-value benchmark task. Receiving a starting value, the agent queries the database and executes recursive searches upon discovering new keys. Standard models fail this immediately. Lacking control over their execution flow, they return the first value they find or hallucinate. This execution flow diagram shows the MEM-GPT agent succeeding. It queries archival storage, pulls the result into working memory, and evaluates if another search is required. The agent successfully loops, holding only the current key in context and evicting previous ones. Kernel-level tool control enables autonomous reasoning over massive datasets that would crash a stateless model. Empirical benchmarks prove that strategic forgetting mathematically outperforms passive, massive context windows. Take the deep memory retrieval benchmark, which tests an agent's ability to recall highly specific facts buried across multiple sessions. This chart shows the baseline collapse. Standard GPT-4 performance drops to a dismal 32.1% accuracy as chat history pollutes the context window. By aggressively swapping data to recall storage, the MEM-GPT agent's accuracy shoots up to 92.5%. These metrics prove a counterintuitive truth. Intelligent data orchestration is superior to attempting to remember everything. This system's theoretical limits are defined formally by the effective context equation. C-fast is the strict physical token limit. H times C-slow represents the retrieval hit rate multiplied by the unbounded capacity of external storage. The efficiency is governed by a corresponding latency equation. By optimizing that hit rate, the amortized cost of accessing infinite memory becomes linear. The system successfully escapes the quadratic O of n squared trap of traditional transformers, operating at a fraction of the cost. Zoom out and you see the life cycle of an OS-backed agent running continuously for years. The main context remains a tight, highly optimized block of active tokens, ensuring the agent never exceeds its thermal or financial compute budget. In contrast, the archival storage scales infinitely in the background, accumulating a massive vectorized history of the agent's synthesized skills and experiences. Moving from stateless chatbots to autonomous agents means shifting away from basic vector search wrappers and toward multi-tiered memory systems. The context window is physical memory, the external databases are the disk, and the language model, equipped with robust tool calling, is the operating system kernel, finally unlocked to run forever.